Hi everybody, my name is Margarita. I'm a master's student at City College of New York, which is a minority serving institution, so money well spent. I am studying environmental engineering, and I will be talking about this new model that came out from NOAA in July called GFS-CMAQ. And what I do is validate it in terms of NO2 and ozone. So first of all, tropospheric ozone is known to aggravate a lot of respiratory illnesses, and it has been linked to pulmonary problems, cardiac problems, to higher depression, anxiety diagnosis. And so being able to predict that is very important in the urban environment. We know that one of its precursors is NO2. So when we're talking about the model, we're interested in seeing, can we predict the NO2 accurately, and also can we predict the second pollutant, ozone? This NOAA FE3 based GFS-CMAQ, of course, became public in July 2021, and it improves the basis for air quality alerts and provides air quality information for people at risk. And the old version you might have known as NAM-CMAQ. So the new dynamic core has changed, and now it's the GFS. And it has a lot of very interesting updates, where the CMAQ portion of it is just the chemical and the transport portion. So the goal of the study is to use integrated remote sensing and ground observations at two sites: City College of New York, which is in Manhattan, and Queens College, which is in Queens. The distance between is a little less than 15 kilometers, but the model that we're working with is providing 12-kilometer resolution. So given that we're not simply working with one point, but we need to work with a grid and figure out how to pull data from the grid and how many grids will fit. Where is the point I'm interested in located in the model? I came up with a normalized weighted average system where I use the resolution to preserve that, 12 kilometers, and I say that the distance from the grid to my point must be 8.5 or less kilometers. And then I weight it and then later average. And the weight is the square distance from the grid and inverse it. The planetary boundary layer that Harold talked about a little earlier, that is the dynamic portion in the lower atmosphere where a lot of mixing is happening during the day. I use telemeters at CCNY and the wind lidar at Queens College for that. It produces data about every 10 minutes. And the Pandora spectrometer, which provides NO2 column, produces minutely data. And I am comparing that to ground observations, NO2 and ozone, and the Tropomi, which is the satellite that makes a single pass, as Harold mentioned, over New York. So there is a very different amount of data coming from all of these sources. So the first thing I want to look at is, how is the model doing in terms of weekend and weekdays trends? Because we know that NO2 is emitted by cars with internal combustion engines. So we understand already that, oh, like, commute probably has something to do with it. Does the model take into account that there is going to be definitely less commute on weekends? Does the model take into account that? So what we see is that the correlation for NO2 is pretty good, ranges between 0.45 and 0.64. And ozone, in comparison, is doing spectacularly well. Everything is above 0.8. We see also some underestimation, especially for NO2. Okay, interesting information. What can we do with that? Next thing we can look at is, I think somebody even asked a question about this, is to break a day apart into these windows of time. We have the 12 to 4, or some people say 11 to 3, the convective window, when the surface gets really hot and there is a lot of convection going on and a lot of mixing. And the shoulders of that are called the transition windows, which is the 7 to 11 a.m. and 5 to 8. But those windows have a lot of traffic going on, especially in Manhattan, Queens. A lot of people are commuting. And what we see is that the model is doing a very good job predicting the trends, the behavior, right, of emissions for the 7 to 11, a little equally, well, 12 to 4, and then worse for 5 to 8. And the same thing we saw in the previous slide, where ozone is better predicted than NO2. So now that we looked at those temporal windows, we're curious in why is ozone better predicted than NO2, and how does the distribution change in terms of the spatial variation? So is it homogeneous on the ground across the whole city? And the first image on your left shows that the model thinks that the NO2 is better distributed on the ground than it actually is when we look at observations. However, the model, once again, for ozone is showing that the correlation is 0.91, 0.95. So this difference can be due to simple emission changes and that ozone takes time. The formation of ozone is not uniform, as we know from the chemical equations. And it is possible that for that equation to take place, some mixing happens in the meantime, and that is why ozone is so much better distributed. Now we're interested in, okay, so we looked at the space, looked at the time, what is happening in terms of the vertical distribution of the gas? Is there a lot on the ground and nothing else is happening in the column, or is it evenly distributed? So what the model tells us is that the Queen's College, in terms of the PBLH, so the height of that dynamic layer, is better predicted. We see some underestimation, but the model overall is pretty close. And we need that now to take into account that the two observation ways that we collected the data, ceilometer and wind lidar, are different. So the ceilometer relies on the aerosols and the wind lidar relies on the behavior of the wind. That might have something to do with how we're looking at the data. Finally, we get to compare this column inside this, taking into consideration PBLH, and the two ways that we can measure column are the Pandora network, which provides us the tropospheric vertical column product, and the Chapomi, which is a satellite. So keep in mind that Chapomi also gives us a single point in a day. So if we're looking at a whole month in August in 2020, there is not a lot of data. And given that the model has a vertical profile, we can use the pressure levels to calculate the column. And when we get to compare it to the observations we have on the ground. And what we see is that Chapomi is actually better correlating with the model than with Pandora, which is pretty surprising to me, at least, because I was under the impression from my previous research that Pandora was more accurate. So as I mentioned, there's really not a lot of data. So if we want to do a more in-depth statistical analysis of all three, Pandora, Chapomi, and the model, this is how many data points we need to work with for the month of August, because all of that needs to be meshed up temporally. But what we can do is look at the surface and Chapomi to actually make sure that the data we're using is accurate. And we want to make sure that what's happening on the surface, at least we have some kind of understanding how it reflects to what's happening in the column. And what we see is from previous research is that Chapomi and the surface are well correlated, even though we're dealing with different units over here. So now the question is, can we compare to Pandora, given that Pandora to the model did not show very promising results? We want to see what is happening on the surface in terms of the observations from the ground and Pandora, and we see that on its own, it is behaving decently. But now if we take into account this very active planetary boundary layer where all of the mixing happens and we normalize our column by that height, we're pretty much collapsing, and it is making our comparison make a little more sense. And what we see is that the correlation improves if we do that, especially for weekends. So something called titration is this behavior of NO2 and ozone, whereas one is going up, the other one is going down. And what we're interested in is observing whether the model can replicate this relationship of NO2 and ozone. And what we see is it's doing pretty well, especially during weekdays, which is expected because we have a lot more traffic during weekdays. And that tells us that, this is a graphic from a different publication. This tells us that our area for the month of August 2020 was NOx limited, where the production of ozone is dictated by NOx versus VOC. Some other regions can be VOC limited. So the model is doing pretty well. The final way I wanted to look at it, at its performance, is given that for ozone to happen, we need sunlight, we need warmth. How does the model behave if we look at sunny and cloudy data? So I manually went over ceilometer images taken at City College, and I picked the time when we have sunny daytime versus cloudy daytime. I split it, and what we can see is that the model, once again, thinks that it is doing so well. And the ground is, I mean, it's pretty close, 0.59, 0.43. The model compares to it pretty well. So to summarize, we see a pretty good, a fair correlation between NO2 that is observed and the model. We see that ozone is doing much, much better. And that is probably because it takes time for the ozone chemistry to happen. We see that ozone is more evenly distributed between the whole city, Queens and Manhattan. The model replicates this titration trend, and it happens especially well during weekdays. At the same time as the trends are replicated, so the peaks can be matched, the model still underestimates the observations. Finally, Pandora, Trapami, the model, we need more data than that. And I am currently working on the August 2021 data. It has equally good performance of ozone. And if you want to hear more about August 2021 data, you can come to my GU talk on May 26th. But the talk is at like 5:30 in the morning Eastern time. So my work was made possible by my NOAA grant. A bunch of people from NOAA helped me, specifically EMC. I did my nurture with them. It was an amazing team under Jeff McQueen. And I want to say thank you to all of the people who made all of these data sets for me available. So New York State of Environmental Conservation, EMC, Trapami people, the Mesonet, the Pandora network. Thank you so much. I can take questions now.
Got a question to kick us off. Got time for a couple questions. All right, George.
Yeah, now GFS-CMAQ is still an offline model, of course, and there'll be in the near future, there'll be an online version of it. How would you expect if you run online, would that change any of the results? Could you empathize about that?
Okay.
If you use an online modeling system, would you expect a possible change in the results, or?
If by the time it goes online, it gets better and gives a better resolution than 12 kilometers. So I know that we're being predicted in 5 years, 3 kilometer resolution. I don't know enough about the details of the model and how it would change if it did go online.
Interesting to see anyway, because it's quite different. Because right now you're still using, CMAQ uses different physics than GFS, and it's using point values every hour, snapshot, temperature, moisture, winds. So it's interesting to see.
Yeah, definitely.
Alaa, did you have a question?
Yeah, no, good talk. There's also Tempo coming. A satellite called Tempo that would give you a little bit maybe information on the resolution. So would you have enough data then to say more about the Pandora versus Tropomi? Because I was curious when you say Tropomi and the model agree,
Yeah.
but the real one, the one that physically based measurement did not agree. So does that point to your model physics, PBL?
Yeah, so I think that to study that better, we need to look at more than just 1 month in 2021. August, like 2020 was important because it is very hot, but if we want to see how the satellites and all of these measurements interact with each other, we also need to look at the seasonal trends. So when I have more data, I will get back to you.
All right. Let's thank our speaker.